In this video I'm going to show you how to set up Solidworks flow simulation, and we're going to run a simple 2D external flow case. I've got a new part open here. I'm going to first set my units. If you don't have this tab showing up that says flow simulation, what you need to do is go up next to the gear to this little drop down menu, add-ins, and look for Solidworks add-ins, flow simulation, and make sure that both this left and right check mark are selected, and then the tab will show up for you. So let's go ahead and draw a simple airfoil just to show you how easy it is to set up flow simulation and how quickly we can get a job running. I'll draw a generic airfoil. It's not any particular type of airfoil, it's just a streamlined body. Okay, there's our airfoil. Now what we need to do is extrude, and I'm going to use the mid plane. What that'll do is make it easier later to set up the computational domain. I'll show you what I mean by that. Okay, there's the body. I'm going to solve the flow around now. Once the body's complete, make sure you save it. And now check the Flow Simulation tab and go to the Wizard. This really makes it easy to set up CFD jobs. Project name, we'll just call it 2D airfoil. Leave everything else as is. Click Next. I like to use foot-pound seconds. Go down here under mass and correct this. I'm an abomination of a pound mass unit to slugs. Go to geometric characteristics, and by default angles are shown in radians. I'm sure you'd like those to measure in degrees. Once that's done, move on. We're going to be solving an external flow problem. The body is solid, so we don't have to worry about any closed cavities. A lot of different features you could select here, different types of flow problems, even unsteady flow, buoyancy problems, rotation, so forth. We'll look at those in later videos. Just click Next now. Got to tell Solidworks what gas you're using or what fluid you're using, so we're going to use air. We're going to allow it to calculate laminar and turbulent. We're going to do a low Mach number test case, so we don't have to select this. Adiabatic wall, we won't worry about roughness now. And here's how you can set up your initial flow parameters. We're going to solve for using velocity, defined by, I like to use aerodynamic angles. Look down here in the lower left hand corner. You see how your coordinate system is set up. It depends on what plane you drew your body on. So in this case, I'm going to want the flow to be in the x-axis. And let's just say it's going to be 100 feet per second. the longitudinal plane is XY. That's correct. The longitudinal axis is X. And we'll allow the angle of attack and side slip to be 0 in this case. Turbulent parameters we'll leave as default for now. And that's it. We've now have a job set up. It's not ready to run yet because there are some things we need to change. You'll notice this is the computational domain that Solidworks set up for this job. It's a pretty poor domain because what you're going to be saying is that this boundary is infinity and it's not influenced by the body. Obviously that's wrong, so we're going to have to change that. So come over here to Computational Domain and right click. You can also do some of these through the icons up here. I've just gotten used to right clicking on these to the left in order, so that's the way I'll do it. Edit Definition. We're going to run a 2D simulation. So we'll click on that first. You notice it changes the computational domain. It's still not good enough, but one thing you'll notice is that in the Z direction, let me rotate it. You see how thin it is? In the Z direction, it's applied what's called symmetry boundary conditions on both sides of the domain. So this is simulating an infinite width for the flow domain, but it only has to solve it one element wide. So it makes it very computationally efficient. You'll notice here, this is the width of the domain, and you just have to make sure that it's on the body of interest. That's why I set up the drawing as a mid-plane drawing. But this is the width of the computational domain, and all you'd have to do is make sure it's narrower than the body of interest. Okay, now what we want to do is make sure that these walls here are far enough away from the body. I like to make sure, as a rule of thumb, for example, that this forward location is about 3 body lengths away. Downstream, I'll make it 6, and then 3 above, and 3 below. And this is about the minimum size we'd want to go. Once again, what you're assuming is that the flow at the boundary is not affected by the airfoil. These boundaries are infinity. So it's not really possible to make a boundary that's too large. It's just more computationally expensive. But it will affect your solution if you make it too small. But this is good enough for our purposes. You click out of it, and there's your computational domain. And you can hide it if you want. You can put it back on. If you right-click on Input Data here, you can select Show Ambient Velocity. You notice I can zoom in here, and this blue arrow shows what direction the flow is going. That way you can check if you got it set up going the right direction. So that looks good. And the next thing, you don't need to change the fluid subdomains. You usually don't use those for external flow type problems. Boundary conditions, once again, usually you typically don't use those for external flow problems, although if you are doing, let's say a propulsion problem where you want to model a jet or something like that in a domain, those are nice to have. But in a general external flow case, usually we don't have to deal with the boundary conditions. Goals are important. The goals in CFD, oftentimes we call these the unknowns. These are the things that you actually want to output. So I'm going to right click on this and insert global goals. And you'll notice there are all sorts of different goals that you can have it track. Typically what I do is have it track the forces. So the X force and the Y force. I don't need the Z force because that's in the out of plane dimension. And I also would like to track the Z torque. That'd be all the information I'd need for that airfoil. Click out of it, and you notice it'll put the global goals on here. You can also use these for convergence, and I'll show you that later. Next thing to do is go down the list and modify your global mesh. So right click on global mesh, edit definition. You'll notice here if you just show basic mesh, this is the starting mesh that SolidWorks has set up for us. And it's not a bad starting mesh. My rule of thumb is that if I zoom in on the body, at the very least, the absolute very least, I'd like to have a starting at least 10 number of elements along, say, the chord of the airfoil. This has many more than that. So this is not a bad starting mesh. I'm actually going to start it coarser just so you can see it refined faster. So this little slider right here, you'll notice it affects the starting mesh by quite a bit. I'm going to go all the way down to 1, make the starting mesh pretty coarse. You may never use uniform mesh. Advanced channel refinement, if you got a complicated body, sometimes that's useful, but we're not going to need that right now. This ratio factor is useful sometimes. If you're getting into relatively complicated bodies where you really need a lot of elements concentrated near the body, what this does is sort of stretch the mesh towards the body. So let's say if I make this 2, you notice what it did. It keeps the same number of elements, but it squeezes them down, makes them tighter near the body and larger out here near the edge of the domain. But this starting mesh is fine. And I can turn off that basic mesh so I don't have to look at that anymore. I can click that. I can hide the computational domain. And so I'm just about ready to start this job. There's just one more thing I need to do. I need to set up the calculation control options. I can either do that by this icon up here, or I can right click on the input data like I've been doing with the other ones. Go to calculation control options here. This tells the flow solver how it should run the job, what it should be looking for, when it should stop, so on. These are the finish conditions or the criteria to stop. You know, this will tell the flow solver when you think it's done. Usually I set it up for all criteria satisfied. In other words, every criteria I set up. Goals convergence, all goals. Yeah, in this case, I'd like all 3 of these goals to be converged before it stops. You can also add iteration or travels, calculation time, all sorts of different things you can use. Now, one thing you're going to need to do first before finishing with this page, you actually need to go to the Refinement tab. This tells you how many times the domain is going to be refined. By default, it's disabled. So let's turn this on. Let's set it to 5. What that means is that any individual fluid element can be subdivided up to 5 times. So it can give you much tighter elements in regions of flow gradients. So you'll notice that as the flow solves, it changes its mesh, and the mesh actually starts to look like the solution. I'm going to say it can do this 5 times. The approximate maximum cells. This is the largest number of cells that you can that the flow solver will ever use. Now, 55 million cells. That's bigger than most computers can handle. As a rule of thumb on this, you're going to need about 6 gigabytes of memory for every million cells. That's approximate, but that's a relatively safe approximation. It'll depend a little bit on the job, and you can experiment a little bit yourself. But for the purposes of this study, I'm just going to use 2 million. The other thing I like to do, I like the refinement strategy to be periodic, based on travels. Travels is the number of times that the flow would move through the domain, through the entire domain. So we'll leave the default parameters here. You'll notice that it won't start refining until it's gone through 2 travels, and then every travel after that it'll refine. And then this relaxation interval just says that, well, once it's done a travel and refined, don't stop right away. At least wait for 2/10 of a travel to see if anything's changing. Now jump back to finishing, and you'll notice a new parameter here. Refinements. You could tell it, hey, I don't want to even consider the flow solver stopping until it gets to, pick a number, let's just say 5. Another thing I've learned here is that goals criteria, the analysis interval, I like to change this to manual and make this number 2 instead of 0.5. By default it goes to 0.5. This has the flow solver average the goals over 2 complete flow travels to check for convergence. Okay, and that's all we need to do on this tab. Refinement is done. Solving, we don't really need to change anything here. These are things that are useful later, in particular if you're doing multiphysics kinds of things where maybe you're doing a heat transfer problem combined with CFD. Saving, one thing I like to do is save the full results periodically, and I'll just base it on wall clock. You can change it on, base it on iteration, but what this does is it says every hour it's going to solve the complete flow solution. So at most, if your computer crashed or something, you would never lose more than an hour's worth of work, which is nice considering the fact that some very large jobs can take days. You don't want to waste that time. Okay, you just click OK, and we're ready for a flow solution. To run a flow solution, all you need to do is click the Run button. Now what I'm going to do is pause it right away because there are some things I want to show you, and it'll run very quickly and I won't be able to show you if I don't pause it. You don't have to do the pausing when you run a test case, so you can neglect that part of it. But I'll go ahead and click Run, and since this is a new job, the only option I have is to solve a new calculation. This is a nice feature if you have access to computers that are faster that you can run off-site. You can set up different machines you can send your jobs to, so you can still use your local computer for whatever you need to do, and the job will run on remote computers. But I'll run it on this computer now, and then just click Run. You'll notice this little monitor window down here. I'm going to suspend this so I can, the monitor kind of defaults to what you had set up last time. I'm going to delete these. Now you notice the job is suspended. That's why you don't see anything changing. The total number of cells for this starting condition is only 4,700 cells. It's tiny. It'll run very fast initially, but I did that on purpose just so you could watch some of the solution. It's already gone 16 iterations just in the time it took me to open this thing up, and it's already gone 0.375 travels. What I'd like to do is insert a goals plot. So I'm going to click on this, and you can plot all your goals. You notice here you're going to get, by default, this normalized view of your goals, and then also current value and average value. Well, this is somewhat useful. I really don't like looking at normalized goals because they're scaled so much that sometimes you're fooled into thinking things are converged. I actually like to go in here and right click on that screen, change this to travels, change the scale mode to the absolute scale, and then usually I pull this length scale down a little bit. And if I apply it, you'll see here that it's rescaled everything, and I can actually see a little bit better what my goals are. I might change this again. I might go in here manually later on and change the min and max, but we'll leave it here for now. Now it's also nice to be able to watch the flow develop itself. So now you come up to this little tab, Insert Preview, click on this, and it says, okay, what plane do you want to look at? So the plane name, actually if you click back here on the Solidworks tab, this green plane, yep, that's the plane I want to see. It's the front plane. So front plane, no offset because it's right in the middle. That's one of the reasons I used the mid-plane offset, so I didn't have to change this. Plane offset. I want to look at velocity, let's say. It shows better gradients than pressure usually, but you can look at all these different things. But let's just look at velocity. And I want the image to be pretty big, so I'll set this to 5,000. That's the biggest you can actually set the image to. It's nice to be able to display the mesh, so you can watch the mesh refine, so I'll click on that. You can also refine the region if you want to reduce the region that you're going to display, but I'm going to show the whole computational domain so you can see that. Click OK. Alright, it won't show up yet until I actually let it run, so let me go ahead and allow the flow to solve a little bit. And now you see the flow is actually solving on this mesh. Let me pause it again so I can show you something else. If you go to Info tab, you see the travels have gone to 1.175. If I unsuspend it, 1.2, you see it growing. When that gets to 2, you're going to get the first remesh. So let's wait for that. Ought to happen any second now. Look down here where it says calculation. Boom, look, it did the remesh. Everywhere there's a strong flow gradient, it starts to put more mesh elements. And so you can see how it refined the domain. It's almost ready to remesh again. And boom, there's another one. You see how much the goals have been changing. And I'm up here to 3.5 travels. Just about ready to remesh again. And there it goes again. And now you'll notice it'll start running slower. Now we're up to 65,000 elements, which is not really that tight, but it's still considerably larger than where it started. I'm going to pause it. Now, your mesh is going to start looking so tight in areas that it's difficult to see the flow. So you might come in here and make another one. And just go ahead and plot the exact same thing, but just turn off the mesh. And if I run that again, you'll see another one will pop up here. And now I can actually see the flow pattern a little bit better, and even start to see the boundary layer and so forth. And this will just get, you know, tighter and more refined as the flow solution runs. Now let's go over and look at these goals. I'd like to look at this area a little bit closer. This is where I might want to change the manual minimum and maximum. You notice I've changed the manual minimum and maximum so I can get a better view on what these unknowns are doing. And you'll see they're definitely not converged yet. Still quite a bit of oscillation. We're already up to about 173,000 elements. You'll notice how much slower it's running now. Look at the travels. If I unpause it now, you can see quite a bit slower. So it's going to take a while to get to the new refinement. This is very often the case. I mean, early on you get a lot of variation, and then these unknowns will just keep changing and floating around. Very often what they'll start to do is level off in between travels, and then sometimes jump when a travel changes and you have a refinement. Don't be fooled into thinking that it's just converged once these level off. Your best indication of convergence is after several different mesh refinements have happened. You don't get any change anymore. And so you might have to run your first test case with any geometry for quite a long time and let it refine to as much memory as you have, and look at the convergence characteristics of the job you're running. So I'm going to let this run for a bit, and then we'll come back and look at it later. I've run this test case for about 15 minutes now, and you see it's gone about 7 travels. Looks here like things are leveling out, but don't be deceived by that. Let's look at a couple of things. Look in the log, and you can see we've had 1, 2, 3, 4, 5, 6 refinement cycles. We're at about 523,000 elements, and you can see here in terms of how many iterations it run, travel, and so forth. What you're going to notice, though, is that the number of elements won't actually get any larger than this, because we've told it don't refine any more than 5 levels. It may be possible that that's not quite enough for this test case, especially since I started with such a coarse mesh. So what would end up happening that you got to be careful about is that you could just let it continue running at this point, and you'll notice everything will just stay flat. But that's because it can't really refine the mesh anymore. It says it's still refining, but it's not really refining the smallest elements anymore. What it's just doing is changing the distribution as the gradients change. So what you can do while the solver is running is go up to calculation, and you can actually change the calculation control options on the fly. I'm going to bump the refinement level all the way up to 7. And I can leave the maximum number of cells the same because I haven't I'm not even close to the limit yet. Now if I was close to the limit, I'd try to bump that up as well. But just change that one parameter, hit OK, and we'll let it run longer, and then I'll come back and show you what the effect was. I've let the flow solver run for about 2.5 hours now, so let's just review where we are. You'll notice now that the total number of cells is about 1.7 million. I've gone about 1,100 iterations, and you can see here in terms of the travel, total time, and so forth. In terms of the number of refinements, 1, 2, 3, 4, 5, 6, 7, 8, 9 refinements, and since we set the maximum number of refinement level to 7, that means that you could take the smallest elements will have been refined up to 7 times. And look what it did to the convergence. Remember where we were before was around 6 to 8 travels, and it was stuck at about 500,000 elements, because even though it was continuing to refine, the refinement level was only set to 5, so the elements were never increasing beyond 500,000. You could see how you could easily be fooled into thinking that this solution was converged, because after 6 travels, there's very little change in the solution. But as soon as we made that change, that was done at number of travels of 8, you see significant changes happened in terms of the goals. The number of elements went from 500,000 to about 1.5 million, and then went up from there at the subsequent refinement. You see big changes in a transient, and then there's certainly a shift in the maximum. So in terms of the y-force, for example, you see where the new leveling is up here, and before we could have been fooled to be thinking it was here. Same thing for the torque and also the x-force. So now what you want to do is you want to make sure that you don't continue to get any kind of changes as the number of elements increased. What I did in this, for the sake of time, so I can get this video out, instead of waiting for 10 travels, I forced a refinement at about 9.5 or 9.6, and I did that by simply hitting this refine button. That's nice in a pinch if you want to do a quick refinement, but probably would have been better off to let it hit 10. But still, you notice even though the number of elements went up, very little change happened in the solution. I'll let it run longer, but I'm pretty convinced that this solution is converged, and these are the actual values that we're gonna get for the unknowns. You'll notice it shows that it's not converged, and that's because we told it to average over 2 travels before it checks for convergence. And you see here it's only been about 1 travel, 1.5 travels maybe, that it's settled down. So I might stop this job manually, but the flow solver won't stop until all of these hit green.